starts. Oh, okay, perfect. So this cup of water might look clean, but there's actually a lot of microplastics and oil that you can find within this. Hello, everyone. My name is Snigtha Mohanraj. I'm a junior at the Engineering and Science University Magnet School, and my project is called the Synthesis of Porous Polymer Sponge Matrix using modified sodium alginate clay compounds for the adsorptive removal of microplastics and oil from contaminated water. So firstly, I'd like to thank everyone that went into making this project a success. Dr. Christine Broadbridge, Mr. Richard Pellegrino, and Dr. Fabian Menges all helped with the outside lab work, and Ms. Alyssa Anderson was my school mentor. And just as a note, all the photos and graphs found within this presentation were created by myself, unless otherwise noted. And just as a note for the Q&A period, if it helps, there are slide numbers in the bottom right corners, so that's just for reference. So the goal of this project was to determine an inexpensive, environmentally friendly, and overall efficient method for removing harmful pieces of plastic and oil from our water through using sodium alginate, Montmorillonite clay, and ionic liquid. And because all of them have favorable properties, it was expected that all three would yield the highest contaminant removal rates. So let's rewind a bit. I've been working in water contamination for a while now. So in 2019, I did my first project using natural coagulants for microplastic removal. And then in 2020, I built on that and used an electromagnetic filter with metal oxides. And then after that, I developed the ferrosponge, which actually just got approved for a patent, and it uses iron oxide nanoparticles and bentonite. The bentonite is key here because it's very similar to montmorillonite. It's a very similar clay, and it actually had inspired its usage in my current research. After that, I used biochar for pharmaceutical and pesticide removal. And then in 2023, I started doing some preliminary research about montmorillonite clay at home for water contaminant removal using a homemade spectrometer I already had. So this is very rudimentary research, but it did inspire what I'm working on now. So my current research investigates combinations of sodium alginate, montmorillonite clay, and ionic liquid in the form of gel polymers in order to remove harmful pieces of microplastics and oil from our water. So why microplastics in the first place? Well, this refers to pieces of plastic that are less than 5 millimeters in size. They can be harmful to us, other organisms, and even the environment. They can cause damage to our internal body structures when digested, but they can also be toxic or transport toxins themselves, like chemicals or biofilm, which is harmful bacteria attached to the plastic. PETE is the most commonly found form of plastic, and that led to its target in my project for removal. Oil is also a very significant and harmful contaminant that can be found in a lot of water sources. It can join water through mass oil spills and also just getting into runoff water, which then contaminates our water supply. It can cause respiratory damage, decrease our immunity, and increase our cancer risk, so it is essential that we remove it from our water. Crude oil is very commonly used and has significant health risks, and that's why I wanted to target gasoline specifically within my project. So the first compound that I'm using in my solution is sodium alginate, which is a naturally found polysaccharide. It's most noted for its ionotropic gelation with calcium ions, and in which it basically forms an interconnected pore network through cross-linking between the ions and the carboxylate groups of the sodium alginate. And this gives ion exchange properties. It's also a very environmentally friendly material, and it has a very high surface area, which means that it's very applicable when using it for water contaminant removal. So montmorillonite clay is a naturally abundant, safe, and inexpensive clay. It also has a very high surface area and stable, and it can add hydrophobic properties to the sodium alginate, which is hydrophilic and not as ideal for water contaminant removal. So it's essential to be removing or using montmorillonite clay in addition. And the ionic liquid is the third component I'm using, which refers to salt in the liquid state at or around temperature. It's been getting a lot of new attention because it's very tailorable, so it can be used in a variety of different applications. It's stable, it has a low toxicity, it's hydrophobic, and increased surface area and stability. And the specific ionic liquid I used is 1-ethyl-3-methylimidazolium acetate, which does not have a very nice name to be using, but it does have a lot of nice properties, like a low volatility, it's biodegradable, and it has shown adsorptive abilities for both organic and inorganic compounds. So I prepared 6 kinds of gels. The first 2 were 0.5 gram and 1.0 gram pure sodium alginate, and I did this alternation between 0.5 and 1.0 to see how that affected results. So then for the next 2, I added the montmorillonite clay, or MMT for short. And then for the last 2, I had the MMT as well as the ionic liquid, or IL for short. And these were all turned into the gel polymers through using calcium chloride. So then I prepared the contaminated samples by mixing PETE and gasoline into distilled water, and these contaminated samples were treated with the gel polymers through centrifugation, and the samples before and after treatment were placed into the UV vis spectroscopy in order to collect data. So the data showed that 1.0 grams, which is a higher concentration of sodium alginate, along with the MMT and the IL added in, created the most effective gel polymer, removing about 78% of microplastics and about 85% of gasoline. I tested two different contact times, 30 minutes and 60 minutes, and 60 minutes was more favorable. And then I did research at 20 degrees Celsius and 40 degrees Celsius. I thought that the higher temperature would speed up the reaction and increase results. However, it is notable to note that the ionic liquids are known to be functional at or around room temperature, which is probably why the 20 degrees Celsius was better to be using in this application. And then there was this characteristic peak in a lot of the samples around 720 nanometers. And like I said, I've been working in water contamination for a while, and I've seen that microplastics in oil are very sensitive within the absorbance values in spectroscopy around the same range. And so that's why I focused on just 720 nanometers here. So this is just composite data, just showing how I got the numbers on the previous slide. This is just here for reference, just talking about the different filtration environments and the different gel polymers. And the bottom right graph just shows 1.0 gram sodium alginate, MMT, and IL, which was the most effective to be using. So this is all for microplastics. Then there's the stuff for oil here. I'm just going to go through this, but this is just here for reference if you'd like to look at it. And then after that, this is also just for reference to show what the UV vis results look like. So there's some data just straight from the graphs or on the software program, and then also the graphs that I generated by using the data for individual trials. And then I did an FTIR analysis to confirm that indeed I was dealing with PETE plastics within my samples. So the black curve is a known PET sample, and then the red is the trial samples that I was using. And I can see how they're pretty much identical, confirming the presence of PETE within the samples that I was testing. So this was just a good confirmation analysis. And then I also compared the sodium alginate, montmorillonite, and ionic liquid compound to alginic acid. And we can see that there is a lot of characteristic curves found in common between the two, confirming the presence of alginic acid. But there is some slight variation, well, not just slight, a lot of variation towards the 500 and 550 range, which is on the far right. But past research has showed that this is pretty characteristic in MMT because of specific bending vibrations. And so this also confirmed the results with the MMT within the compound. I'm still in the process looking for ionic liquid to confirm that, but unfortunately because of the snow day, that got delayed a bit. But that is what I'm working on right now. And I also did a scanning electron microscopy using a tabletop SEM to analyze the surface structure. And as the MMT and IL were added, there was definitely increasing porosity and textured surfaces, which made it more ideal to be using. And I imaged each sample at 400, 1000, and 3000 magnifications. And I'm currently working on energy dispersive X-ray to further analyze the composition of the gel polymers. So these are some of the images I took. The left column is just sodium alginate. The middle is sodium alginate and clay, and the right is sodium alginate, clay, and ionic liquid. The top row is 400 magnification, the middle is 1000, and the bottom is 3000. And when we look at just the sodium alginate, MMT, and IL column on the right, with the increasing magnifications, we can see it's very rough, it's very textured. There's a lot of pores, making it very ideal to be using. And these pictures just showed the SEM instrument and me driving the SEM. I just thought they were cool to include, so here they are. And then again, the results just show that sodium alginate, MMT, clay, and an ionic liquid is an effective way to remove microplastics and oil from water. And who knows, maybe other contaminants as well. So with the abundance of sodium alginate and MMT, this method is very cost-effective and easily implementable on both small and large scales. And the gel polymer is very flexible and versatile, so it can be used in a variety of different scenarios. So I'm currently working on a dip coating methodology for synthesizing the prototype, which is noted for being able to provide more stability to the compound I'm using. So instead of like a flimsy like gel polymer, actually using a sponge or metal mesh backbone to provide more stability. And in this application, I'm specifically working on using a melamine sponge, soaking it in the solution, and then adding the calcium chloride to create a coated sponge in the end. And that top photo shows the melamine sponge, but also metal meshes that can be used in replacement. And then this is a design that I made in previous years for a household filtration system. So I made this in the past, but I do think it's very helpful, and that's why I'm trying to build on it, because the compartment system means that I can use sand in the top compartment to remove larger contaminants like plastic and glass. And then my past research has showed that biochar is very effective for removing other contaminants like pharmaceuticals and pesticides. And the melamine dip-coated sponge using the sodium alginate, clay, and ionic liquid would be found at the bottom. And the reason why I want to include all three in one filtration system is because the people most affected by the water contamination issue do not have access to any kind of treated water. And by using this filtration system, we can protect these people most at risk at lower costs. And then there's also,
you just have a couple, just 2 minutes left.
thank you. And then this obviously needs to be having more refinement, and you can't really just throw these sponges out in the water, but there could be simple ideas just like lining water dams with melamine sponge barriers, or even treating the water directly in order to protect the local water body ecosystems. And also, this is where we get our drinking water from, so it's important to just keep these water sources clean. So there are larger applications that can be applied as well, because the dip coating methodology with the sponge provides a lot more stability and flexibility. And so for future research, I definitely want to further develop the prototype through dip coating, achieve a 100% removal rate, and look at other contaminants. Unfortunately, I didn't get to look at reusability that much, but I have seen that ethyl acetate can be used to cleanse the gel polymer and probably this dip coated sponge as well. So I'm looking into that more. And I only tested 2 temperatures and 2 contact times. So I'd like to investigate that further to find the optimal points where I can maximize effectiveness without using too many resources. And so this is a graphical abstract just to cover what I've done basically in this project, which was mixing the sodium alginate montmorillonite clay and ionic liquid in a solution, magnetically stirring that, freeze drying, adding it to a calcium chloride solution, freeze drying it again, and then cutting it, taking that to measure in the SEM and FTIR analyses to look at the composition, but also using those components to treat the microplastic and oil contaminated samples, centrifuging it, and then putting it into the UV-vis spectroscopy to collect data. And so to briefly conclude, many people lack access to clean drinking water, especially in underprivileged communities that do not have access to any form of treated water. My research has showed that a gel polymer composed of sodium alginate, montmorillonite clay, and ionic liquid can be an efficient method to protect us from some of the most prominent examples of harmful contaminants like microplastics and oil in our water. This is a cost-effective, environmentally friendly, and easily implementable method. Thank you for listening to my presentation, and if you have any questions, I would love to answer them.